Measures of dispersion. In this segment, we look at measures which tell us how spread out or dispersed our data might be. The most basic measure of dispersion is the range, and this simply tells us the difference between the maximum and minimum values in a data set. So if we have the following data set, the smallest value is -5, the largest value is 25, so our range is 30. Next, we look at the mean absolute deviation, or MAD. This is the average of the absolute values of the deviations from the mean. The way you solve this problem is fairly straightforward. Say you have the following data. The first thing you need to do is compute the mean. So the mean for this data is the sum divided by 4. So the mean is 10. We then need to take the average of the absolute deviations. So the absolute deviation for the first data point relative to the mean is 0. For the second data point, the absolute deviation is 15. For the third, it is 0. And for the fourth, the absolute deviation is again 15. And we need to take the average, so we divide by 4. We have 30 over 4, which is 7.5. Now do this practice question where you are given a data set and you need to find the mean absolute deviation. Here is the answer. The first thing you do is come up with the mean, which is 75.6, and then you take the average of the mean absolute deviations, and then you take the average of the deviations from the mean. And when you take the deviations, you have to take the absolute value of the deviations. So this is exactly the same as what we have done earlier. Your answer should be 36.5. Next, we talk about population variance and standard deviation. This is the most important measure of dispersion. Population variance is the mean of the squared deviations from the mean. The population variance is computed using all members of a population. Let us take the same data set that we looked at earlier and say this represents the return on 4 stocks which are in your portfolio, and if your portfolio only consists of those 4 stocks, then that essentially is our entire population. Now, how do we compute the variance? In a few slides, I will show you the formulas, but at this stage, let us understand the concept. We are essentially looking at the deviation from the mean. So obviously the first thing to do is to compute the mean, which we have done earlier. The mean is equal to 10. The next thing we do is come up with the mean of the squared deviations from the mean. So what are the squared deviations from the mean? For the first data point, the squared deviation from the mean is 0. For the second data point, the squared deviation from the mean is 15 squared, because the deviation of -5 from 10 is 15, and we square that gives us 15 squared. Then the deviation here again is 0, and with 25 we have 15 squared. So we need to find the mean of these squared deviations. So we just add them all and divide by 4, and we get 112.5. So this is the population variance. The population standard deviation is defined as the positive square root of the population variance. So we simply take the positive square root of 112.5 and we get 10.6. So 10.6 is a measure of how spread out the data is around the mean. Now take this hypothetical set of companies. We are given the yields, and what you need to do is come up with the population variance. And remember, you need to first find the mean, then the deviations from the mean, square the deviations, and then find the average or mean of those squared deviations. Here is the somewhat ugly looking formula that I was referring to earlier, but notice this formula is doing exactly what I said. X represents each value, so I is equal to 1 to n, that's each value, minus the mean. The mean in this particular case is 14.71, and we are taking x minus the mean squared. This is the summation sign, so we are summing up all the numbers and dividing by n. So notice here, 10.5 is our first value, which is this one, minus 14.71, which is the mean, and then we square that, and we do the same for all the other values, these numbers, and then we add up those numbers and divide by 5 because we have 5 observations, and we then come up with the population variance. If we need the standard deviation, that is simply going to be the square root of 45.20. And notice, by taking the square root of 45.20, we come up with a number which has the same unit as the mean. Next, do this problem where again we have 4 companies, here is the data, and now you need to find the population standard deviation. So essentially you find the variance and then take the square root. So the same formula, except we now have the square root. You find the mean, and then inside the square root sign is essentially the variance. By taking the square root, you come up with the population standard deviation. Now let's look at the sample variance and standard deviation. The point now is that a sample variance applies when we are dealing with a subset or sample of the total population. So if your total population now is defined as all stocks on a given stock exchange, and you pull out 4 stocks and you have the return on those 4 stocks now represent a sample, and the formula that we use or the mechanism that we use to calculate the variance is slightly different. What we now do is almost the same as what you saw earlier. As we did with the population, the first thing we need to find is the sample mean, which is 10. We then find the deviations from the sample and square those deviations. So 0, 15 squared, 0 and 15 squared, and then we find the mean of those deviations, so we divide. But the difference now is this: rather than dividing by n, which is 4, we need to divide by n minus 1. So this is 3, and that is the convention used when we are dealing with a sample. At this point, you don't need to get hung up with the reason for why this is done. Just take it as a given that when you are dealing with a sample, then you have to divide by n minus 1. So the value that we will get for the standard deviation and the variance will be higher. Once you have a value for the sample variance, you can find the sample standard deviation by simply taking the positive square root of the sample variance. Now let's do this problem. You are given the following companies and you are given the dividend yield, which is very high, but nevertheless, let's look at these numbers. The sample variance, notice, is the same formula except for the n minus 1. X bar is the sum of observations divided by number of observations. X bar is the symbol that we use for a sample mean, which is 14.71. Then the variance is the deviations from the mean squared, added up across all data points, and then divided by n minus 1. The sample variance is 56.49, and if we want the standard deviation, that is equal to 56.45. Now let's look at the use of the calculator. Take the same return data and we need to find the population and sample standard deviation. Here are the keystrokes. Second, data to enter into data entry mode. So second, and then data, which is right here. Then you need to type second clear work. This will clear all the data registers. Then you put in 10, that's this number right here, and enter. That sets your first data point to 10. Down arrow once and then a second time. When you put down arrow once, you will see Y01. But since we are only entering one set of data, you do not need to enter any information for Y. So we just down arrow past the Y. Then you will see X02, enter 5 plus minus. That is essentially then saying that the second data point is minus 5. You do the same for 10 and 25. You have now entered the 4 data points into the calculator. Then you hit second stat. This puts the calculator into statistics mode. And what you might see is uncertain. Either you might see 1-V, which stands for one variable, or you might see ln or something else on the display. What you need to do is keep hitting second set, second over here set, until you see 1V. This stands for one variable. Since you are doing one variable calculation, the calculator should be in a single variable or one variable mode. Once you see this, you should press the down arrow, and what you will see is n equals 4. This is telling you that we have 4 data points. You press the down arrow again and you will see X bar equals to 10. That is telling you that the mean of this data is 10. You press down arrow again, you will see SX equals 12.25. There might be more decimal places depending on how your calculator is set. So this stands for the sample standard deviation. The calculator obviously doesn't know whether this is a sample or a population. So it says that if these 4 data points are a sample, then the standard deviation is 12.26. And then you hit down arrow again, you will see this symbol. Notice this is the Greek symbol. So this is the population standard deviation. Assuming these 4 data points represent a population, then the standard deviation is 10.61. The calculator doesn't give you the variance, but if you want to find the variance, you can simply take this number and square it for the population variance, take this number and square it for the sample variance. Let us now talk about Chebyshev's inequality, which essentially states that for any set of observations, the proportion of the observations within k standard deviations of the mean is at least 1 minus 1 over k squared for all k greater than 1. To understand this concept, let's say you have the following data. You have mean is equal to 20 and let's say that the standard deviation is equal to 3. We want to find out what percentage of the data must reside between two standard deviations from the mean. So we know that our mean is 20. Two standard deviations to the right of the mean would be 2 multiplied by the standard deviation number, which is 3. So that is 6. 26 is 2 standard deviations to the right of the mean, and similarly 14 is 2 standard deviations to the left of the mean. So the range 14 to 26 represents plus or minus 2 standard deviations from the mean. So what percentage of the data must lie between 14 and 26? In other words, what percentage of the data must lie between 2 standard deviations from the mean? And that is what Chebyshev tells us. K is the number of standard deviations from the mean, which in our example is 2. So the number of observations that must lie within 2 standard deviations of the mean is equal to 1 minus 1 over 2 squared, 1 minus 1 over 4. So this is 0.75. In other words, Chebyshev's inequality tells us that at least 75% of the data lies within 2 standard deviations of the mean. Now this can also mean that we have more than 75% within 2 standard deviations of the mean. But we can know for sure that it is not possible to have only 50% of the data within 2 standard deviations of the mean. This inequality is so powerful because it tells us for sure how to measure the maximum amount of dispersion regardless of the shape of the distribution. Notice that here we don't make any assumptions about whether the distribution is normal or not normal. This inequality applies across all distributions. Let's see if you can solve this problem now. Notice that when you plug in 3 over here, where 3 is the number of standard deviations, you will get 0.8889. So what that essentially means is that if we go 3 standard deviations from mean, we will cover at least 88.89% of the data. Moving now to the coefficient of variation. Coefficient of variation expresses how much dispersion exists relative to the mean of a distribution and allows for direct comparison of dispersion across data sets. It is used in investment analysis to compare relative risks. A simpler way of putting it is that the coefficient of variation is simply your variation per unit of return. In other words, if your coefficient of variation is high, that means that the investment is relatively risky because for every unit of return you have relatively high variation. So let us look at a simple example. You have investment A with a mean return of 7% and a standard deviation of 0.05. The coefficient of variation for A is going to be the standard deviation, which is 0.05, divided by the mean return. Since this is a percent, we need to convert it to a decimal, so that is 0.07. The coefficient of variation for B is equal to the standard deviation, which is 0.07, divided by the mean return, which is 0.12. The investment with the higher coefficient of variation is more risky. So you actually need to solve these two and figure out which one has the higher coefficient of variation. Investment A has a higher coefficient of variation and is therefore more risky. In case you forget whether the numerator or the denominator is this variation in the formula, The simple way to think of it is that the name is coefficient of variation. The emphasis is on variation, so we use variation or the standard deviation in the numerator. Now look at this example where you are given 3 bonds and you need to figure out the coefficient of variation for all 3. You simply need to divide the standard deviation by the mean. Notice here that I am using the percentages, and that's okay as long as we are consistent and both the numerator and denominator are using a percentage. The question asks for the lowest risk. Lowest risk would mean lowest coefficient of variation, and that would be B. The Sharpe ratio. The Sharpe ratio tells us whether a portfolio's excess returns are due to smart investment decisions or a result of excess risk. The Sharpe ratio is simply the return on a portfolio minus the risk-free rate divided by the standard deviation of the portfolio. So this is the excess return, and that is divided by the variation. So if you have a portfolio with a return of 10% where the risk-free rate is 4%, the excess return is 6%, we need to divide that by the standard deviation of the portfolio. Let's say that the standard deviation of the portfolio is 12%. This would mean that the Sharpe ratio is 6% over 12%, which is 0.5. Now this in of itself doesn't tell us whether the Sharpe ratio is good or bad. You need to compare with other portfolios. If you have another portfolio where the Sharpe ratio is 0.7, then this other portfolio is giving us a better return relative to risk. The way you can think of this is we are determining through the Sharpe ratio our excess return per unit of risk. And obviously it is better to have higher return or higher excess return per unit of risk. Let us solve this problem now. We are given 3 portfolios and we are given the mean returns and the variance for all 3 portfolios. You want to determine which has the highest Sharpe ratio. In other words, which portfolio is giving us the highest excess return per unit of risk. So all we need to do is the following. We take each return, subtract the risk-free rate and divide by the variance. If you do the calculations, you will notice that portfolio A is giving us the highest return per unit of risk and is therefore the best portfolio. Notice that we are given the variance numbers, which means that we have to take the square root of the variance to come up with the standard deviation. Symmetry and skewness in return distributions. Skewness or skew refers to the extent to which a distribution is not symmetric. Now, when you have a normal distribution, it has a skewness of 0, or we can say that a normal distribution is symmetric. What that means is we have an equal distribution on each side of the mean. This could be your mean, this is also the median, this is also the mode, and the distribution on each side is the same. This is symmetric, so the skewness is equal to 0. A positively skewed distribution is characterized by many outliers in the upper region or the right tail. This is called the right tail. Notice that we have several outliers over here. This is called a right skew. When you have a right skew or a positive skew, these outliers on the right pull the mean to the right. So the mean is going to be greater than the median, which is over here, which is going to be greater than the mode. Mode is the most frequently occurring item, so that is over here. This is the mode, and we essentially have this relationship where the mean is greater than the median, which is greater than the mode for a positively skewed distribution. For a negatively skewed distribution, we have a large number of outliers on the left. This is the left tail. What this does is pull the mean to the left. Therefore, in this situation, we have a mode which is greater than the median, which is greater than the mean. Let us look at a practice problem. Which of the following is most likely characterized by frequent small losses and a few extreme gains? We have just seen this. The correct answer is C, positively skewed, where we have a few large losses and many extreme gains, which represents the outliers on the right. Which of the following is most likely to be true for a negatively skewed distribution? And we just saw this. In a negative skew, you have a relationship like this, where the mean is pulled out to the left, the mode is over here, and the median is in the middle. So you will have a situation where the mean is less than the median, which is less than the mode. Now try this one. The correct answer is A. Moving now to kurtosis. Kurtosis is the degree to which a distribution is more or less peaked than a normal distribution. Now just take this as a given that a normal distribution has a kurtosis of 3. A kurtosis is a measure of how peaked a given distribution is. So this is a normal distribution with kurtosis equal to 3. If you have a distribution which has fatter tails and is more peaked than normal, such as this one, this has excess kurtosis. Let's say this has kurtosis equal to 5. The excess kurtosis is 5 minus the normal of 3, which is 2. Excess kurtosis here is equal to 2. When a distribution has excess kurtosis, we say that it is leptokurtic, and you just need to remember that. A normal distribution which has a kurtosis of 3 is called mesokurtic. A leptokurtic, as I have already said, is more peaked and has fatter tails relative to a normal distribution. Platykurtic means that kurtosis is less than 3. A platykurtic distribution is less peaked relative to a normal distribution. These are the core points that you need to remember with regards to kurtosis. Here are the sorts of questions you might see on the exam. Which of the following is most likely to be a measure of when a distribution is more or less peaked compared to a normal distribution? So all you really need to do here is remember the term. The correct answer, as you have just seen, is C. A distribution identical to a normal distribution is, and here again you just have to remember the fact that a mesokurtic distribution has a kurtosis of 3, and this is your normal distribution. The final section in this very long reading now, using geometric and arithmetic means. A geometric mean is appropriate for making investment statements about past performance. Now let us look at a straightforward example. Say you had $100 2 years ago and you had a return of 100% in year 1 and minus 50% in year 2. What was your mean return? If you simply take the arithmetic mean, then you will have 100 and then minus 50. So that is 50 divided by 2, which is equal to 25%. So the arithmetic mean is 25%. But look at what's actually happening. When you have $100, in the first year you get 100% return. So you end up with $200 at the end of the first year. But then in the second year you lose 50%. Which means that you are back down to 100. So in reality, you have not made any money. You started with 100, you end up with 100, so your mean return really is 0%. Arithmetic mean, however, is telling you that the return is 25%. So clearly the arithmetic mean is not the right measure when you are looking at returns over a period of time. A better measure is the geometric mean. So let's look at how we would calculate the geometric mean. If you recall, with geometric mean, you do 1 plus the return in the first year. 100% return means you just do 1 plus 1. Remember, a 50% return would have meant that we do 1 plus 0.5. So 100% return means that we do 1 plus 1. And then you multiply by the return for the second year, 1 plus the return for the second year, which is actually minus 0.5. And then you raise to the power of 1 over 2. We have 2 multiplied by 0.5 raised to the power of half. So what you have is 2 times 0.5 is 1. 1 to the power of half is still 1. And then you minus the 1 to get a rate, and you end up with 0. So your geometric mean is 0, which means that on average you are getting a 0% return, and that is a much more accurate depiction of what is happening. An arithmetic mean is appropriate for making investment statements in a forward-looking context. If you have $100 now and the two possible returns for the upcoming year are a 100% gain or a minus 50% loss, what is the expected value? Here it makes sense to look at the arithmetic mean of 100 and minus 50 and to say that our expected return is 100 plus minus 50 over 2, which is equal to 25%. So saying that our expected return is 25% is appropriate. However, in the first scenario where we have time series data, there the appropriate measure is the geometric mean. So that is it. We are done with this reading. Just a few major summary points. We talked about measures of central tendency, and here you need to understand the various kinds of means. We talked about arithmetic mean, we talked about geometric mean, harmonic mean, the weighted average, and so on. You need to understand all these different kinds of means and how to calculate them. Then we talked about measures of dispersion. The most important measure is standard deviation. This tells us how spread out our data is. You need to know how to use the formula, but it is more important that you understand how to use the calculator to determine standard deviation. Recognize also that standard deviation is different for a population versus a sample. You also need to understand Chebyshev's inequality, which is 1 minus 1 over k squared. The k stands for the number of standard deviations, and the strength of Chebyshev's inequality is that it allows us to say how much data will be within a certain range, assuming without making any assumptions about the nature of the underlying data. You should also be on top of the Sharpe ratio as well as the coefficient of variation. And finally, you need to understand the basics of skewness and kurtosis. In terms of the work that you now need to do, go over the learning objectives outlined in the curriculum, go over the examples and practice problems, especially the shorter problems or the multiple choice oriented problems in the curriculum. The other questions might look a little bit difficult, and that's okay. At least read the solutions and try to figure out what the curriculum is trying to say. I would say it is more important that you do practice questions from other sources like Schweser, and try to do as many questions as possible to make sure that you are on top of this material. That is it.